Okay, this is a video on a review for C3 and C4. Review for C3C4 for the test that's happening tomorrow, Thursday, March 29th, period 2. Okay, so we're going to go over the 4 kind of topics that we had in this unit, which are just equations of lines, equations of planes, intersections between a whole bunch of stuff, and distance from a point to a plane. So it's like 4 sections for this video. Okay, so part 1, let's just talk about lines. Okay, so we're talking about lines. So we got lines that are happening in 2 space, and we got lines in 3 space. So if we're just doing 2 space, then we got an x and a y plane, whereas in 3 space, we've got an x, y, z plane. So x, y, z. Okay. So a line in 2 space could look like this. And we can write equations of lines in 2 space. We can write them as vector equations, scalar equations, parametric equations, and symmetric equations. So I'm just making these up. They have nothing, they're not actually the equation of the line I just drew. But let's start with a scalar equation. So say we had, I don't know, 3x plus y equals 6. So say that's the equation of this line, which it's not. I'm going to redraw that line. Okay, so 3x plus y equals 6. So this is our scalar equation of a line. So we also have a vector equation of a line. So if I wanted to switch that to a vector equation of a line, I know a vector equation has to have a point and a direction vector. Okay, so I just need any point on that line, and I need a direction vector. And in 2 space, a direction vector is pretty much just like the slope. So if I just took the scalar line and rearranged it into y equals mx plus b, I would get y equals negative 3x plus 6. So the slope of my line is negative 3. And this number here tells me the y-intercept. So I know my line's going through 6, and then it's going like down 3 over 1. So my line looks kind of like that. So since I know the slope of my line's negative 3 over 1, I could say, so that's like the rise, and that's the run. So if I wanted to make a direction vector, run is like my x, and rise is my y. So I could make my direction vector 1, negative 3. So it's like going over 1, down 3. Well, that's going up 3, but anyway, say it was like that. So then our line would be like that. So it's almost like the components of the vector is your slope. Okay, so there's my direction vector. And then a point on the line could be my y-intercept. So I know at my y-intercept, x is 0 and y is 6. Or if I didn't want to use that point, I just plug anything in for x and y to make that equation's left side equal the right side. Okay, cool. So that's a vector equation. So I got a scalar equation, a vector equation. I can turn my vector equation into parametric equations by just splitting these up. So x here is 0, and then 1t. So I write 0 plus 1t. Or I could just write that as x equals t. I don't have to write the 0. And then y equals 6 minus 3t. Those are my parametric equations. And I could also write a symmetric equation. So to write a symmetric equation, I just isolate t from my parametric equations. So x equals t is already isolated. And for my y equals 6 minus 3t, I just isolate t. So 3t equals 6 minus y. So t equals 6 minus y divided by 3. So once I isolate t, I just can set those equations equal to each other since the t's have to be the same if they're the same equation. So I would just say x equals 6 minus y over 3. So this would be my my symmetric equation. And then my symmetric equation, that can help me go back to my scalar equation if you didn't know what your scalar equation was, just by rearranging this symmetric. So I could multiply by both sides by 3 to get rid of the denominator. So I'd get 3x equals 6 minus y. And then if I just want to rearrange it, I get 3x plus y equals 6, which is, boom, the equation we started with. So that's lines in two space: scalar, vector, parametric, and symmetric. And I can check if a point's on a line. So if I wanted to say, hey, is the point 1, 1 on the line? Okay, so I could do it a couple ways. If I had the scalar equation, I would just sub it in and see if the left side equals the right side. So like 3 times 1 plus 1 equals 3 plus 1, which equals 4. And that does not equal 6, which is what my equation equals. So not on the line. If I didn't know my scalar equation and I just knew my parametric equations, for example, so x equals t and y equals 6 minus 3t, I only knew those things, I would just sub my point 1, 1 in for x and y and see if my t's equaled the same thing. So negative 5 equals negative 3t, so t equals 5 over 3. Not the same. So it's not on the line. All right, cool. So that's 2 space. So then 3 space equations of lines. You can't have a scalar equation. No scalar equations exist for 3 space for lines. Okay, so you can only have vector equations, parametric equations, and symmetric equations. So to write the vector equation of a line in 3 space, it's the same thing. We just need a point on the line. So let's make it up, 1, 2, 0. And we need a direction vector. So like 4, 1, negative 2. So point and a direction vector. And that describes what the line is like, which I just, again, that line doesn't match the equation. Okay, so that's our vector equation in 3 space. And parametric is the same. So you just write x, y, and z. So x would equal 1 plus 4t, 2 plus t, and z is 0 minus 2t. So those are our parametric. And then our symmetric, we just isolate t. So for my top one, t would equal x minus 1 over 4. And y would be t equals y minus 2. And z would be t equals z over negative 2. And symmetric ones, we just equate all the equations. So we just say x minus 1 over 4 equals y minus 2 equals z over negative 2. So those are the symmetric equations. So that's a line in 3 space. So we can't do scalar, we can just do vector, parametric, and symmetric. Oh, and I could give you information, like I could give you 2 points on the line. So say I said, hey, there's a point A, which is like 1, 0, 5. And there's a point B, which is negative 1, 2, 3. So I've got like these 2 points. And they lie on a line. And I want to know, hey, what's the equation of that line? And I just know 2 points on the line. So we know to write the equation of a line, we need a point right there. And we need a direction vector. So it's almost like kind of like the slope. It tells us the direction that the line's going. So we know a point, A and B, so we could just take one of those. Cool, whichever one. And we just have to figure out our direction vector of our line. So what you could do is, since you know 2 points on the line, you could get that vector. So you could figure out the vector AB, which is just negative 1 minus 1, so negative 2, 2 minus nothing, 3 minus 5, So there's a direction vector, and if I wanted to, I could reduce my direction vector to lowest terms. So I could make it -1, 1, -1. Just divided it all by 2. So there's a direction vector. So if I was given 2 points, I could easily make the vector equation of a line, and then I can make the parametric and symmetric equations from that. Or I could give you some random information, like I could give you a point on a line. So I could say, hey, this point 1, 1, 3 is on a line. You're like, okay, cool, I got a point. And then I could give you some other information like, oh, also this line is parallel to this other line. Or it's perpendicular to this plane. So you could be given information, and as long as you have that point, when you're making your vector equation, since you have the point, you can just stick that in there. And then it's just your direction vector you have to figure out. So if it's telling you it's parallel to something, that means it's going to have the same. So if it's parallel to something, it's telling you it's going to have the same direction vector as that thing. So if I give you the equation of another line, you can just steal its direction vector, whatever it is. Or if I'm telling you it's perpendicular to something, then its direction vector is going to be perpendicular to that thing. So, or for example, if I told you it was perpendicular to a plane, well, that's crazy because the equation of a plane, these points right here, or these coefficients, are the normal vector, which is perpendicular to the plane. So you can actually just use the normal vector for your direction vector. So you just have to like see what information you're given, and you know you need a point and a direction vector. And however you get those, there's like a million different ways. All right, cool. Moving on. Section 2. Already 12 minutes in. Holy moly. Okay. Section 2 is planes. All right, so the equation of a plane, you can have scalar vector equations and parametric equations of planes. But normally you see planes as scalar equations. So let's start with that. So we use the pi symbol to represent a plane. So let's say we had a plane that was like 2x plus y minus z plus 3 equals 0. So there's the scalar equation of a plane. So one thing you should know for sure is the normal vector of this plane. So we should know the coefficients in front of x, y, and z create the normal vector, and the normal vector is perpendicular to our plane. So if we had a plane, the normal vector is something that shoots off that's 90 degrees to the plane, perpendicular to the plane. That's our normal vector, 2, 1, -1. Okay, so this is the scalar equation of a plane, or Cartesian equation, or standard form. There's like a bunch of different ways to say it. Things that we can do if we wanted to find points on the plane. So let's say we wanted to find some points on this plane. We just sub stuff in to make our equation equal 0. So I could just say, okay, I want x to be 0. I want y to be 0. And I want z to be 3. Because I know 0 plus 0 minus 3 plus 3 will equal 0. Cool, so I know that's a point on the plane. I'll call that point A. Then I'll make another point on the plane. So maybe I'll make it -1. 1. No, just kidding. 0, 1. Okay, does that work? Because that would be like -1 times 2. So -2 plus 0 minus 1. So I got -2 minus 1 is -3 plus 3 equals 0. Cool, that works. So I just found 2 points on the line. I could find another one. Let's do 0, -3. Ooh, wait. Let's make that 1. Because then I'd have like 2 minus 3. And we'll make that a 2. So 2 minus 2 will go away, -3 plus 3. Okay, cool. So that's another point. So you just kind of sub stuff in for x, y, and z so that this equation will equal, like left side will equal the right side. All right, so I found 3 points on the plane because I wanted to. And it could help me. So if I wanted to take the scalar equation of a plane and put it as a vector equation. So the vector equation of a plane looks like this. It's got a point. So we'll have a point, x, y, z, plus 2 direction vectors. Because it needs to, or else it won't be enough information. Okay, so then it has 2 direction vectors. All right, so if we wanted to take this scalar equation of a plane here, 2x, whatever, that guy, and make it into a vector equation, so all we really know is a perpendicular vector to the plane, this guy, but we don't want that. We want to know 2 direction vectors that are on our plane and a point. So we can do that by, I found 3 points that are on our plane. So these 3 points, so if we had a plane, these 3 points would like exist on the plane. And from those 3 points, well, one of them we can stick in to use as our point. So like 0, 0, 3, we could stick in there. And we need 2 direction vectors. So you can use your points, A, B, C, to create a vector like vector AB, vector BC. So you can use your points to create direction vectors. So if I wanted to create vector AB, that would be negative 1 minus 0, 0 minus 0, 1 minus 3. And then vector BC would be 1 minus negative 1, 0. Negative 3 minus nothing, 2 minus 1. So that would be the 2 direction vectors that I got. So then I could just plug those into my vector equation. All right, so I got the scalar equation of a plane, and I just turned that into the vector equation of a plane. And then if I wanted to get parametric equations of the plane, I would just write like x equals 0 plus negative 1t plus 0s. Y equals 0 plus 0t minus 3s, like a weird equation. Z equals 3 minus 2t plus s. So those would be my parametric equations. Parametric equations of my plane. Okay, and we don't have symmetric equations for our plane. Okay, so that's planes. Oh, let's talk about how to go from a vector equation to a scalar equation. So if you were given a vector equation of a plane, so let's say I just made this vector equation up of a plane, and it was 1, 2, negative 1, plus s, 1, 4, 5, plus t, 1, 2, negative 1. All right, so there's a vector. Actually, I don't even want any negatives because I'm being really lazy. 1, 2, 3. Awesome. Okay, so there's the vector equation of a plane. So let's say I wanted to turn that into the scalar equation. So I know a scalar equation looks like Scalar equation looks like ax plus by plus cz plus d equals 0. And I know a, b, and c are my normal vector. A, B, C. So I need to figure out a vector that's perpendicular to my plane. So since I have 2 direction vectors here, so that's like if I had a plane, these vectors would lie right on my plane. And I know if I put them tail to tail, if I did the cross product between those 2 vectors, it will give me a vector that's actually perpendicular to both of those, which is called the normal vector. So I'm going to do the cross product between this guy and this guy so that I can find my normal vector. All right, so I'm going to cross product those guys. So I got 1, 4, 5, 1, 4, 5, 1, 4, 5, and I got 1, 2, 3, 1, 2, 3. Okie dokie. So cross product will give me the normal vector. So 4 times 3 is 12 minus 10. And then 5 minus 3. 2 minus 4. If I did that right. Hopefully. So 2, 2, negative 2. Weird. And then I could just reduce that to lowest terms if I want to. So just be like 1, 1, negative 1. So you can just kind of factor out the 2 there. So I'm going to use that as my normal vector. So when I'm writing the scalar equation of a plane, I just use that as my a, b, and c coefficients. So I'd get x plus y minus z plus d equals 0. So that's my scalar equation. I just need to figure out what d equals. So to do that, x plus y minus z plus d equals 0. I just take a point that I know is on my plane. So, hey, why not take this point? 1, 2, negative 1. And we'll sub that in for x, y, z. So 1, 2, what was the other one? Negative 1 minus negative 1 plus d. So I sub that in. So I get 1 plus 2 plus 1 is 4. So I figure out that d is actually negative 4. So when I sub that back in, the equation of my plane is x plus y minus z minus 4 equals 0. So that's the scalar equation of my plane. Given we had originally had the vector equation, and we just cross product it to get the scalar equation of a plane. And if you wanted to figure out if a certain point is on a plane, I think it's similar to lines. You just kind of sub your point in for x, y, and z and see if the left side equals the right side. All right, cool. So that's lines and planes. 21 minutes in. Should I pause it? No. Let's keep going. Okay. Part 3. Intersections. Okay, intersections. Okay, intersections could happen between 3 different things. So they can happen between lines, they could happen between a line and a plane, or they could happen between 2 planes. Whoops. Okay, sorry. All right, cool. So lines. So we could have lines in 2 space. Let's just call 2 space r squared and 3 space r cubed because that's shorter. So in 2 space, they could be parallel, or they could be coincident, so they're essentially the same line, or they could be intersecting, so they cross and they intersect at a point. So things we know about that is these guys would have the same direction vector because they're parallel. Oh, coincident lines would also have the same direction vector. And intersecting lines would have different direction vectors. So for these guys, parallel and coincident, since they have the same direction vectors, you'd have to figure out which one it is. Is it parallel or is it coincident? And you could test that out by seeing if, like, you know, a point from this line is also on this line or something. All right, and then in 3 space, you got the same options. So you have parallel lines, which would have the same direction vector, or like a scalar multiple of a direction vector. Coincident lines. Or you could have intersecting lines that intersect at a point. Or you have this 4th case that's like skew lines. So we'll call this skew. And they actually don't intersect. But they also they're also not parallel. Okay, so when you're solving those kinds of questions, intersections of lines, because I don't have time to actually solve any, when you're solving them, you want to get them into parametric equations for each line. I'm just pretending they're in 3 space, but they could also just be in 2 space. So you want to get their parametric equations for each line, and then you want to sub them into each other. So if this was like x equals 1 plus 2s, and this is 3 minus t, to sub them into each other, I'd be like 1 plus 2s equals 3 minus t. So your kind of solution method is subbing the parametric equations into each other and solving for s and t, and then subbing s and t back into your parametric equations to figure out your point of intersection, if it exists. Okay, cool. Lines and planes. So they can intersect, like, they could be parallel. So you could have a line that's parallel to the plane, in which case, yeah, they would be, they would have the same direction vectors, but if you can't tell what the direction vector of your plane is, because sometimes you can just tell what the normal vector is. So if you knew the normal vector, it would have to be perpendicular to the direction vector of your line. And you could tell they're perpendicular by maybe doing the dot product of them to see if they equal 0. Okay, you could also have coincident, so the line could actually be on the plane, in which case it'd be the same thing as above. Or a third case, they could be intersecting. So you could have a plane and a line that intersect at a point. And to solve that kind of question, to find out where the intersection between a point and between a line and a plane is, you just sub them into each other. So you take your line in parametric form, so you figure out what x, y, and z equals in parametric form, and then you take your plane in scalar form. This is just one way to do it. I'm just making this up. And you would sub in the parametric into the scalar equation and kind of solve for t or s. And then you could sub that back into your parametric equations to figure out your point of intersection. Okay, two planes. So things that could happen with two planes are they could not intersect, so they could be parallel like the other stuff, in which case their normal vectors would be the same. So if you're looking at the equations of two planes, their equations would be pretty much identical except for the constant. Or you could have the same planes, so coincident planes, in which case their equations would have to be identical or scalar multiples of each other. Or you could have intersecting planes that are super hard to draw. It's lunchtime. I gotta go. Okay, so you could have two planes that intersect, and it's weird, but they intersect in a line. This one's kind of weird to solve. So you're given like equations of two planes, so 2x plus y minus z plus 3 equals 0. I'm totally making these up. X minus y plus 2z minus 6 equals 0. So you got the equations of two planes, and you're trying to figure out where they intersect in a line. And this one's weird because two equations, three unknowns, you're not going to solve for a point. You're solving for a line, so you have to introduce a parameter. So you kind of have to like do elimination, like say you want to add these equations together. So you got 3x, y plus negative y would be nothing, negative z plus 2 would be 1, 3 plus negative 6 would be negative 3. So you solve and you get 3x plus z equals 3. And now you want to introduce a parameter. So you want to say, okay, I'm going to let x equal t, or z, whatever. So I'm going to let x equal t. So now I know that z is actually equal to negative 3x, or negative 3t, plus 3. So you've actually got almost all of your parametric equations. You found x equals t, z equals this, and now you can just go back to an original equation to solve for y, and you've actually figured out the equation of this line. So it's kind of weird that you have to introduce this parameter into it, but you have to do that with two planes. Okay, so that's your intersection questions. The only other thing is distance. Just kind of try to get this done. This is like a 30-minute video, which is not bad for like 3 weeks of work. Okay, the distance. So if you have a plane and you have a point, this question is hard. So you don't want to like memorize steps. You want to understand it. We're trying to find the shortest distance from this point to this plane. Shortest distance is always the perpendicular distance. And we're trying to figure out what the heck is that point. So if we know this point is 1, 2, 3, 4, because I wrote 4. 1, 2, 4. We want to know what is this point. I'm just writing x, y, z because I do not know. So we want to know, we want to figure out this point, because in order to find the distance, we do Pythagorean theorem. So the distance is going to be like, you know, x squared plus y squared plus z squared. We're going to like subtract the x, y, z's. But we need to know that point. The only way to figure out that point is to figure out, hey, where does this line intersect this plane? Right at that point. So we need the equation for this blue line. So to get the equation of a line, we need a point, which we have, 1, 2, 4. And we need a direction vector, which we also have, because if we're given the equation of this plane, which we are, 2x plus y minus z equals 4. So you actually know the direction vector for this line because it's actually the normal vector. It's perpendicular to this plane. So the normal vector is 2, 1, negative 1. So there you go. We got the equation of this blue line. And now we just have to go back to what I was talking about for intersections, and we have to figure out where does this line intersect the plane. So we've got to figure out where they intersect. They intersect right at this dot. So we want to put this line in parametric form. Sub it in for x, y, and z. Solve for t. Sub it back into your parametric and figure out this point. Then you can get your distance. Boom. C3C4. Hope it helps. Good luck studying tonight. I'll be on the hub / my email, so send me a message if you need some help. Good luck.
Yes, I be your woman. Yes, I be your baby. Yes, I be whatever that you tell me when you're ready. Yes, I be your girl, forever your lady.
Did you read my message?